In resonant series LCR circuit, the current across the circuit is maximum at certain frequency. A. Find the condition of resonance LCR circuit. So in this question, okay, we have LCR series circuit at resonance condition. So given, okay, and this question we have LCR series circuit at resonance condition. So we have this. Now, question A, find the condition of resonance LCR circuit. So we have to find the condition at which the resonance occurs in LCR series circuit. So I'm writing over here. We have to find the condition, okay? We have to find the condition at which resonance occurs in LCR series circuit. Clear? Now, we know the impedance, okay? We know impedance Z, okay, of LCR series circuit is Z equals under root R square plus XL minus XC whole power 2. I'm drawing LCR series circuit, okay? Resistor having resistance R, inductor having inductance L, and capacitor having capacitance C, okay, are connected in series, and the combination is finally connected to the AC source. So this is LCR series circuit, okay? Now, at resonance, okay, we find inductive reactance equals capacitive reactance, okay? So I'm writing over here, inductive reactance XL equals capacitive reactance, that is XC. Therefore, we can write at resonance XL equals XC. So this is the condition, okay? Condition at which resonance occurs in LCR series circuit. So we have this. Now, I'm writing over here. Therefore, from this expression, okay, we get Z equals under root R square plus XL minus, I'm going to put the value of XC equals XL. So we have XL. Clear? So we have this. Therefore, we can write Z equals under root R square. So we have Z equals R. So at resonance, the circuit is purely resistive, okay? So I'm writing over here at resonance, okay? Circuit is purely resistive. Clear? We have this, and this is the minimum value of impedance. Okay, so this is minimum value of impedance. Therefore, we can write Z equals Z minimum equals R. So impedance is minimum at resonance. Therefore, current is maximum at resonance. So we can write over here, current is maximum, okay? Or I'm writing in this way, at resonance, current is maximum. So this is to be noted, okay? And the series resonant circuit is also called acceptor circuit. So let me write over here, series resonant circuit is also called acceptor circuit. So we need to note this. Clear? So what conclusion can we draw? At resonance, we have inductive reactance equals capacitive reactance, and at resonance, impedance is minimum, and at resonance, the circuit is purely resistive. Okay, and at resonance, the current is maximum. Now for solution of B, deduce the condition of minimum current in LCR circuit. Okay, so we have to find the condition at which current is minimum. Clear? So next, B, condition of minimum current. Okay, condition for, I'm writing in this way, minimum current in LCR, okay, circuit. That is in LCR series, okay, since we have series circuit given in the question. Now I'm writing over here, okay, at resonance, okay, current is maximum and Z is minimum. So we have this, and we are asked to find the condition for minimum current. So it means that the circuit is not at resonance. So the circuit, okay, is not at resonance. So we need to note this, okay, for this question, okay, and we know impedance, I'm writing over here, Z equals under root R square plus XL minus XC whole power 2. So we can write in this way also, R square under root R square plus XL is omega L minus XC is 1 by omega C whole power 2. So we have this. Clear? Now we know in resonance Z is minimum. Clear? Now for this condition, okay, Z is not minimum. So we need to keep in mind that Z is not minimum. Okay, so if capacitance of capacitor increases, okay, if C increases, then 1 by omega C decreases, okay, so this decreases. So if this decreases, then Z, that is impedance, increases. Therefore, impedance Z increases. And if impedance increases, then current decreases or becomes minimum. Okay. So I'm writing over here. Then current decreases or current is minimum. Okay. So we have this. Clear? So we are asked to find the condition for minimum current. So in order to have a minimum current, C must increase. Okay. And if C increases, then omega C decreases. So due to this, okay, Z increases, due to which current decreases or current becomes minimum. So we have this. Solution for question C. Okay. So let us look to the question C. Construct the graph and phasor for inductive dominance. Second, capacitive dominance. Third, resonance condition in this combination. So we are asked to draw the phasor diagram. Okay. So we are asked to draw the phasor diagram for inductive. Okay. For inductive dominance. For inductive dominance, XL is greater than XC. So this is to be noted. Okay. So we have this. Okay. Now we know, okay, Z, that is impedance. Okay. Equals under root R square plus XL minus XC all square. And the phase is given by the relation. Okay. Phase is given by relation tan phi. Okay. Equals, we have this VL minus VC divided by VR. Okay. So we have this relation, and we can further write this relation in this way also. Tan phi equals, we know VL. Okay. This is I times XL minus I times XC divided by I times R. On simplification, we can simply write in this way. Okay. I, and we have XL minus XC divided by I times R. So this cancels out. Therefore, we can write tan phi equals, I'm writing in this way. Okay. VL minus VC divided by VR equals XL minus XC divided by R. So we have this relation. Okay. This is to be noted. And we have this. So we have this. Now, in case of phasor diagram, resistance, voltage, phasor, VR equals I times R. Okay, we have this. Inductor, voltage phasor, this is VL equals I times XL. Okay. Capacitor, voltage. Okay. Phasor, this is capacitor voltage phasor. So this is VC equals I times XC. We have this. For series LCR, we have same current phasor. The current phasor is same for all circuit element, okay? For all circuit elements. So we need to understand, okay, these facts. The voltage, source voltage phasor, okay? Let me write in this way, source voltage phasor. So the source voltage phasor V equals, okay? So this is under root, we have VR square plus VL minus VC whole power 2. So we have this. Therefore, we can write V equals under root, and we know VR is IR. So we have this IR power 2, and we have VL. This is I times XL, okay? So we have this minus I times XC and whole power 2. So we have this. Clear? So we can simplify and write V equals, I'm taking I out of the square root. So I can write in this way. Okay. Now, this term, okay, is called the impedance. So we have this. Okay. So this term is called impedance Z. So we have this. Therefore, we can write V equals I times Z. Okay. So this is source voltage phasor. So what is this? This is called source voltage phasor. So we have this. So these are the basic concepts we need to understand before discussing the phasor diagram. Okay. Now, let me erase this first. Okay. And write in this way. Terms to understand before discussing phasor diagram. So this is more appropriate. Okay. So we have this. Clear? Now, one, okay. C1 for inductive dominance. Okay. For inductive dominance, we have XL greater than XC. Let us draw its phasor diagram. Okay. Let us draw it phasor diagram. Clear? Next, for capacitive dominance. Okay. We have this XL less than XC, or we can simply write in this way also, XC greater than XL. So we have this. And next, for resonance. Okay. So next for resonance. Okay. So we have this. Clear? Now we know in case of resistor or resistance, okay, the voltage phasor and the current phasor are in same phase. Okay. So they are in same phase. So I'm drawing in this way. Okay. Current phasor and this is voltage phasor for resistor or resistance. So we have this. Clear? So this is voltage phasor for resistance. So we have this. And as I said earlier, all circuit elements have same current phasor. Okay. So I'm writing over here. All circuit elements have same current phasor. So we have this. And what is VR? Voltage phasor. This is I times R. Okay. So we have this. And this angle is omega t. Okay. So we have this. Now for inductor, okay, the inductor voltage phasor leads current phasor by 90. So we have this. For inductor, okay. So this angle is 90 and this is VL I times XL. So what is this? This is inductor voltage phasor. Okay. This is inductor voltage phasor which leads, okay, leads current phasor by 90°. So we have this. Now we go for capacitor. Okay. And we know capacitor voltage phasor lags current phasor by 90°. So we have this. So we have this. Okay. We have this. Since the circuit is inductive dominance. Okay. So we have VL greater than VC. So we can see the length of the arrow. Okay. Clear? We have this. Now this is VC. Okay. So this is capacitor voltage phasor. Okay. This lags current phasor by 90°. So we find this. And what we find is that, okay, what we find is that when we look into this phasor diagram is that, okay, VC is always anti-parallel to VL. Okay. VC is always anti-parallel. We find they are directed opposite and they are lying in the same line. Okay. Is always anti-parallel to VL. So this is to be noted. Okay. So we have this. Clear? Now We need to find this, okay? VL minus VC. We need to find VL minus VC. Clear? Now, let me make this more long, okay? So this gives VL minus VC. And we can see the phasor, okay? And this angle is also 90 degree, okay? Capacitor voltage, phasor lags current phasor by angle 90 degree. So what we find in this case is that, okay, I'm just making this, okay? Now what we find, this phasor, okay, this phasor is always perpendicular to phasor VR, okay? We need to note this. So next I'm writing phasor VL minus VC is always perpendicular, I'm writing symbolically, to phasor VR. So we have this. So these are the information, okay, we get from the phasor diagram. Now we have to find the resultant of VR and VL minus VC, okay? So the resultant is this, okay? So this is voltage phasor of the source, okay? So V equals I times Z. So we have this. We have this, okay? So this is what? This is source voltage, okay? This is source voltage phasor. So we have this. Now, this angle, okay, is phi, and phi is positive. So we have phi positive, okay, for inductive dominance. We can see for inductive dominance, okay, we get phi positive, okay, we get phi positive for inductive dominance. So this is about inductive dominance. Now we go for capacitive dominance, okay? For resistance or resistor, current and voltage phasor are in same phase, okay? So this is VR equals I times R. So we have this. Now the circuit is capacitive dominance, okay? So we need to note this. So this is inductor voltage phasor IXL, and we know VC and VL, they are anti-parallel, okay? So we find this. This is capacitor voltage phasor, and when we look into this phasor diagram, we find VL leads current by angle 90 and VC lags current by angle 90. Okay, so we have this. So this is to be noted, and they are lying on the same line in opposite direction. So we have this. Okay, this is to be noted. Now we need to find the difference. Okay, we need to find the difference VL minus VC. Okay, so this gives, okay, this gives the difference VL minus VC. So we have this. Okay, now the resultant of VR and VL minus VC is this. Okay, so this is the source voltage phasor. So this is V equals I times Z. So we have this, and phi in this case, okay, phi in this case is negative. We have XL less than XC for capacitive dominance. So phi is negative. So we have this. This is phi. Okay, so phi is negative, and this angle, okay, is omega t. So we have this. Okay, now what we find in this case, okay, source voltage. Okay, so we have this source voltage phasor. Okay, phasor lags, this lags the current phasor. You can see it lags the current phasor. This is current phasor. Okay, lags the current phasor. So we have this lags the current phasor, and we find phi, okay, is negative, or I'm writing in this way, is negative angle between 0 and minus 90 degree. So we have this. So this is to be noted, okay, for capacitive dominance. So we have this. Now we go for resonance, okay, and we know at resonance, okay, at resonance we have this XL equals XC. So for this reason phi is 0. Okay, we can look in this expression. Okay, when XL equals XC, then we have phi equals 0. Clear? We find this, and Z is minimum, and the minimum value of Z is R. So we have this. So the phasor diagram for resonance in LCR series, okay, LCR series is, okay, of this nature, is of this nature. This is for Z equals R. Okay, so we have this, and this is XL, and this is XC. So we have this. So this is the phasor diagram for resonance LCR series circuit. Now next we have to plot the graph. Okay, we have to plot the graph and show inductive dominance, capacitive dominance, and resonance for LCR series circuit. Clear? Now graph, okay? What we find is that, okay, at frequency below resonance, we find resonance at particular frequency, okay? So at frequency below resonance, we have this XC greater than XL. We have this, okay? So we have capacitive, okay, dominance, or capacitive reactance dominance. So I'm writing in this way, capacitive reactance dominance, okay? So in this case, this dominates. So we find this. Clear? So it means that the voltage lacks current. It means voltage lacks current. So this is to be noted, okay? And phi is between 0 and minus 90. So we have discussed this. So we find this, okay? Next, above resonance. So we have this XL greater than XC. So we have inductive reactance dominates the circuit, okay? So I'm writing over here, inductive reactance dominance, okay, in this case. So what you find, for inductive reactance dominating the circuit, we find voltage leads current and phi is between 0, okay, is between 0 and plus 90 degree. So we find this. In this case, we find phi between 0 degree and minus 90 degree. And in this case, we have phi between 0 degree and plus 90 degree. So we find this. Now let us plot a graph, okay? So this is frequency and we have impedance Z in vertical direction, okay? So we find graph to be of such nature, okay? We find this. Now at resonance, okay, impedance is minimum and the minimum value of impedance is R, okay? So we find this. So we find this Z is minimum, okay? So we find this. So this is the frequency corresponding to resonance, okay? So we have this. So this is for series resonance, okay? Resonance, LCR series resonance. So what we find at frequency below the resonance. So at frequency below the resonance frequency. So in this region, okay? In this region, we find XC is greater than XL. That is, we have capacitive reactance dominating the circuit. And in this region, okay, for frequency greater than the resonant frequency or frequency above resonance, okay, we have this XL greater than XC. Clear? So we have this. So in this case, we have, okay, in this case, we have inductive reactance dominating the circuit. So we have this, and this value of impedance, let's say impedance, is called dynamic impedance. So this is called dynamic impedance. So in this graph, we have shown resonance, okay, at which Z is minimum, and capacitive reactance dominating and inductive reactance dominating the circuit. So we have this.